Section: Introduction. In this section, we discuss the significant advancements made possible by large language models, LLMs, in cross-modality tasks. By aligning visual encoders with LLMs, we have developed visual language models, VLMs, that offer a range of impressive capabilities for visual tasks. These include following instructions, generalizing without prior examples, learning from a few examples in context, and possessing enhanced world knowledge. Over the past 2 years, the field has seen rapid progress, leading to effective training methods and model designs. However, despite these advancements, the human-generated datasets and tasks we rely on remain relatively simple. Given the high costs associated with training VLMs, most approaches use large-scale image-text pairs for initial training, which are often of lower quality. This is followed by a more detailed fine-tuning process with smaller, high-quality datasets. Creating millions or billions of high-quality image-text pairs requires a significant amount of human effort, which is often impractical. Recent methods have explored the potential of using advanced commercial models like GPT-4v and Gemini for distillation, but their performance is limited by these models. At the same time, there is a lack of research on how to better utilize VLMs to address human errors and improve the simplicity of dataset tasks for better training outcomes. In our work, we seek to determine whether VLMs can help overcome dataset limitations and enhance training. We explore the potential of using VLMs to refine and expand pre-training data and performance in an iterative manner. Our new training approach consists of 2 main steps: a self-augment step and a specialist-augment step. We begin with the self-augment loop, which uses VLMs to improve the quality of pre-training data. We show that combining synthetic data with original data can lead to stronger models through a bootstrapping process. We have observed that while these loops provide performance improvements, the benefits tend to diminish after 3 iterations. To encourage further learning, we introduce a more challenging task-specific loop. In this loop, a specialist model, which focuses on new knowledge or tasks, is fine-tuned from the self-augmented VLM using a limited amount of additional supervised fine-tuning data. This specialist can then recaption a large volume of pre-training data. Finally, we can retrain the self-augmented VLM on the newly recaptioned data to further enhance performance. We demonstrate the advantages of this approach using 3 different specialist VLMs that specialize in spatial awareness, optical character recognition, OCR, and grounding. Our innovative VLM augmentation training method progressively improves data quality, enhancing visual semantics and reducing inaccuracies, as shown in our figures and detailed in our experimental section. This leads to a direct performance boost for VLMs. We introduce a new family of models called VILA2, or VILA2, which stands for VILA Augmented VILA. VILA2 surpasses state-of-the-art methods across key benchmarks, achieving this enhancement through self-bootstrap training without unnecessary complexity. Now recognized as the new benchmark leader on the MMMU benchmark among all open-source models, we hope that sharing the insights, recipes, data, and code for VILA2 will help our community better understand and utilize synthetic data to train more powerful VLMs. In our methodology, we focus on autoregressive VLMs, where image tokens are transformed into the textual space and combined with text tokens. We chose this approach for its flexibility in handling multimodal inputs. We follow a widely accepted 3-stage training process: alignment, pre-training, and supervised fine-tuning. We begin by self-augmenting VLM training through a bootstrap loop that leverages the VLM's general captioning abilities. Once this bootstrapping reaches its limit, we introduce specialist augmentation, utilizing the skills learned during supervised fine-tuning to provide feedback for the pre-training stage. We will elaborate on these steps in detail. For self-augmenting through general knowledge enhancement, we note that existing VLM training heavily relies on internet data, which often consists of brief text descriptions. For instance, the average length of captions in certain datasets is less than 20 words. Additionally, human annotations may not fully capture the diverse meanings an image can convey. For example, one caption might only mention a person riding in the street, neglecting details about their clothing or surroundings. Previous approaches have either tasked humans with writing more detailed captions or relied on commercial APIs for image descriptions. The first method can be labor-intensive and expensive, while the second may carry biases from the models used and could raise copyright concerns. We believe that detailed information is crucial for effective VLM training. Instead of relying on proprietary models or manual labor, we aim to use VILA to generate improved captions for its pre-training. We start with the original dataset and train an initial version of VILA, which we refer to as VILA0 in our experiments. We then use VILA0 to recaption the pre-training datasets. By selecting appropriate prompts and conversation templates, VILA0 can produce longer and more detailed captions. The augmented datasets, which include real images from the internet and synthetic texts generated by VILA0, are then reused to train the next version of VILA, called VILA1. This self-augmenting process can be repeated several times until we reach convergence, as illustrated in our figures. Section Summary. In this section, we explore the potential of using visual language models, VLMs, to enhance the quality of training datasets through a self-augmenting process, where VLMs generate detailed captions for images, thereby improving model performance iteratively. Our approach involves a two-step training regime that combines self-augmentation with specialist feedback, leading to the development of the VILA2 models, which outperform existing methods on key benchmarks by leveraging synthetic data for stronger VLM training. Section: Prompts and Template Design. In this section, we enhance our prompt styles within the self-augmentation loop to create a variety of caption styles. This strategy results in immediate improvements in performance. Our main goal is to enrich the knowledge contained in new captions while avoiding repetitive outputs. To assess our design choices, we conducted a detailed study on different prompts, where we indicate the spot for image features with less than img greater than, and we will share our findings. We started with a simple prompt, less than img greater than describe the image briefly. Then, we moved to a longer prompt, long v1, less than img greater than describe the image in detail. Next, we introduced long v2, less than img greater than elaborate on the visual and narrative elements of the image in detail. Finally, we created long v3, less than img greater than instead of describing the imaginary content, focus only on what can be confidently determined from the image, avoiding itemized lists and minimizing aesthetic descriptions. We found that brief recaptions were not helpful. Our initial straightforward prompt asked the visual language models, VLMs, to provide a brief description of the image. Although these brief recaptions were significantly longer than the original texts, 90 words compared to 17, there was no significant improvement in VLM benchmarks. In fact, some metrics even worsened in benchmarks like Science Image and MMMU. This decline was likely due to a lack of detail and the potential for inaccuracies during recaptioning. Next, we redesigned the prompt to encourage VLMs to give a more detailed description of the visual narrative elements in the images. We also referred to the prompt template from SHAREGPT4V to ensure accuracy and precision in the descriptions. Our experiments showed that using 3 different long prompts improved the quality of recaptioning and enhanced performance in benchmarks, with a clear ranking among them. Therefore, we decided to use a mix of these prompts by randomly selecting from versions 1 to 3. We also recognized the importance of keeping the original human text. We compared different conversation templates, where one used only real human data and another combined both human and synthetic descriptions. Our experiments indicated that using self-augmented data improved major benchmarks like LLAVA Bench, Science, Text VQA, and ME. However, we still observed declines in several metrics, which led us to combine both the original and recaptioned texts to best preserve information. This approach consistently improved all VLM metrics. With the right prompt choices and template designs, self-augmentation can continuously enhance caption quality. Our findings showed that synthetic captions became much longer and more informative than real human texts, as reflected in the VQA-V2 score. We also followed LLM Judge to compare caption quality from different rounds, finding that both Gemini 1.0 Pro and GPT-4V preferred captions generated by our method, showing a higher win rate. As we continued, we noticed that the improvements from self-augmentation began to plateau after a few rounds of bootstrapping, suggesting that we had maximized the benefits. We hypothesized that this limitation arose from the repetitive nature of general descriptive captioning, which is heavily influenced by language modeling. To address this, we proposed adding extra task-specific knowledge to the generalist VLM, creating several specialist VLMs. Each specialist model is fine-tuned with data that requires a deeper understanding of image components and semantics, such as spatial relations, localization, and optical character recognition, OCR. It might seem that we need a separate specialist model for each task, but we demonstrated that quick fine-tuning of the VLM during the supervised fine-tuning, SFT, stage is sufficient. A bootstrapped loop can then transfer this specialist knowledge from small-scale SFT data to a large number of pre-training images. This way, we can effectively utilize the abundance of images available during pre-training alongside the specialist knowledge gained during SFT. In this paper, we focus on 3 challenging tasks that require direct visual understanding: understanding spatial relations, grounded narration, and OCR. To specifically challenge the model's spatial awareness, we created a dataset called Spatial Relation QA, which includes 1 million conversations about spatial relations within scenes. This dataset is based on LV3D, a comprehensive collection of both indoor and outdoor 3D datasets from Cube LLM, designed to enhance the understanding of 3D spatial relations that require perceptual and grounding skills. We developed a 3-step process to create question and answer pairs. First, for each cleaned 3D scene, we examined all 3D bounding boxes and randomly sampled from 5 object-object relations, like closest, in front of, behind, left, right, and 6 object-camera relations, such as close, far, closest, farthest, left, right. Next, we checked if any remaining bounding boxes matched these sampled relations. Finally, when a match was found, we randomly selected question templates to construct the QA pairs, incorporating instances, their projected 2D bounding boxes, and relations. For example, a question could be, where is the chair closest to the table, given its coordinates in the image, with the answer being the target bounding box. Section Summary. In this section, we explore the design of prompts and templates to enhance the quality of image captions by diversifying styles and incorporating detailed descriptions, which leads to improved performance in various benchmarks. We also introduce specialist VLMs fine-tuned for specific tasks like spatial relations and OCR, leveraging both self-augmented data and human-generated texts to optimize captioning accuracy and information retention. Section: Grounding Specialist. In this section, we focus on enhancing grounding awareness through a method called grounded narration. This task is very visual and requires visual language models, VLMs, to create detailed captions that help locate important visual elements using 2-dimensional bounding boxes. This method gives us thorough supervision and helps us check if the VLMs are generating accurate information or hallucinating. To build our VILA2 grounding specialist, we utilized image caption pairs from the 20 million GRIT dataset. First, we filtered out bounding boxes that covered more than 70% of the image, as many images in GRIT were book or album covers that didn't closely match the captions. Next, we eliminated images that had more than 3 instances of the same category to simplify the data and reduce noise in the generation process. This filtering resulted in 4 million higher quality instances for training our grounding specialist, which we then divided into 2 groups: grounding short with 3 million instances and grounding long with 838,000 instances for a 2-stage fine-tuning process. Next, we turned our attention to strengthening our OCR, optical character recognition capabilities. We gathered a diverse collection of images that included text, such as tables, charts, and documents, to create an OCR specialist. Each image was annotated with question and answer pairs that focused on text recognition, comprehension, and reasoning. For example, we might ask, what is the title of the book? For recognition, which bar has the largest value? For comprehension, and what is the main idea of the quote from Albert Camus? For reasoning. More details about the dataset can be found in the appendix. We then applied these three specialists in the final augmentation stage. To do this, we used a new set of task-oriented prompts to activate their knowledge and enhance their ability to follow instructions by narrowing their focus. For instance, we prompted the Spatial Relations Understanding Specialist with templates like, elaborate on the visual and narrative elements of the image in detail, focusing on spatial relations, and, can you explain the content of the image and their spatial relations in detail? During this augmentation stage, the grounding specialist generated captions with bounding boxes for the main visual elements, while the OCR specialist identified most of the text in the images. We curated the responses from these different specialists into question and answer pairs and added them to the original captions of Koyo images for the next iteration of VILA2. More details can be found in the appendix. Moving on to our experiments, we followed the architecture from VILA, which consists of three main components: a large language model, LLM, for generating text, a visual encoder for extracting visual features, and an image text projector to align the visual and text modalities. For our exploratory experiments, we used Llama 2 to 7B to investigate how much a VLM can self-boost. We then switched to our previous state-of-the-art settings with Llama 3 to 8B instruct and Yi34B for comparisons with other methods. For visual encoders, we employed SIG-LIP for the Llama series models and Intern VIT6B for the Yi34B model. We adapted simple linear layers for the projection layers to connect the image and text modalities, following the LLAVA approach. Additionally, we introduced a 4x downsampling of visual tokens by combining 2x2 neighboring patches along the channel dimension and using a simple multi-layer perceptron for the downsampling process. In terms of training strategies, we conducted VILA2 training using a widely accepted three-stage approach. In the first stage, we initialized the projector randomly while separately pre-training the language models and the visual transformer, VIT. To align the feature space between the visual and text modalities, we used the LLAVA alignment dataset. In the second stage, we pre-trained the model, including the LLM and the projector, on a visual language corpus, which included interleaved image text data and image text pairs. We applied our VILA2 approach to the pre-training data, replacing the original Koyo captions with the augmented data. Finally, in the third stage, we performed instruction tuning of the pre-trained model on visual language instruction datasets. The blending details are included in the appendix. Unless stated otherwise, our experiments were conducted using 128 GPS with a global batch size of 1024. We used the AtomW optimizer with learning rates of 1 × 10 to the power of -3, 5 × 10 to the power of -5, and 2 × 10 to the power of -5 for the three stages, respectively. Each stage was trained for one epoch with a 3% warm-up strategy, and we did not apply weight decay. In some cases of self- or specialist-augmented training, VILA2 may involve an additional stage for further improvement. For more details, please refer to the relevant sections and the appendix. For our pre-training stage, we used 6 million samples from MMC4, 25 million samples from Koyo, and the complete Sharev dataset. To ensure a fair comparison, we only replaced the text captions during our experiments while keeping all image sources the same. We created two blends of supervised fine-tuning (SFT) data for different purposes, a smaller blend of 1.8 million samples for exploratory experiments and a larger blend of 5.9 million samples augmented from VILA's training recipe for state-of-the-art experiments. Detailed information about the SFT recipe can be found in the appendix. Section Summary. In this section, we describe our development of specialized models for grounding and OCR tasks, utilizing filtered image grounded caption pairs and diverse textual content images to enhance visual and textual understanding. We detail our training strategies, including a 3-stage process for aligning visual and text modalities, and the use of task-oriented prompts to improve the model's instruction following capabilities. Section: Specialist Setups. In this section, we integrated specialized data with high-quality image captioning datasets and various instruction fine-tuning datasets. This approach ensures that our models maintain their storytelling and instruction following skills while also gaining knowledge specific to certain tasks. For the spatial specialists, we continued training from Stage 2, using the ALAVA caption and the GPT-4V caption from ShareV. In the case of the grounding specialist, we divided the cleaned 4 million grounded narrations into 2 parts, 3 million for grounding short and 838,000 for grounding long, to facilitate a 2-stage training process. In Stage 3, we combined the grounding short with the ALAVA caption to adapt to new grounded narration tasks while preserving narrative abilities. In Stage 4, we merged the grounding long with Shikra GPT-4, Visual 7W, LLAVASFT, and 100,000 GPT-4V captions from ShareV to maintain both narrative and instruction following capabilities. For the OCR specialist, we trained it using various internet datasets that focus on text recognition, understanding, and reasoning. This included datasets like LLAVASFT, Text OCRV, Synth DOGN, OCRVQA, Text Caps, Archive QA, DOCVQA, AI2D, Chart QA, LLAVAR, and 35 OCR-related datasets from the Cauldron. In our evaluation, we tested our models against several common visual language model benchmarks. Due to space constraints, some metrics are abbreviated. These benchmarks include VQA version 2, GQA, Science QA, Text VQA, POPE, MMBench, MMBench Chinese, SeedBench, LLAVA Bench, In the Wild, MMVet, and MMMU. Regarding our self-augmentation results, our aim is to enhance existing pre-training datasets by rewriting captions to make them denser and more informative. Instead of relying on human effort or opaque APIs, we utilized VILA to generate these captions. This enriched captioning helps in developing better VILAs, which can then provide feedback to further improve the captions for the training dataset. The main performance boost for our visual language model comes from the improvement in caption quality. As shown in our results, the average word count in captions increases significantly after self-augmentation, peaking around the 3rd and 4th rounds. Initially, in the first round, the caption length jumps from 12 to 101 words, while in the 3rd round, it only increases from 117 to 126. After the first round, the increase in caption length becomes less significant, but we still see consistent improvements in the visual language model benchmarks. We believe that self-augmentation after the first round mainly enhances caption quality, providing more accurate details and reducing inaccuracies. For example, the original caption for a given image is brief, only mentioning Boris writing action. After one round of self-augmentation, the caption becomes longer and much more detailed, including descriptions of clothing and the surrounding environment. Some inaccuracies are also introduced, such as incorrect details about the suit color and a basket that isn't visible in the image. As we continue self-augmenting, these inaccuracies gradually disappear. By the 3rd round, the captions only describe visual elements we are confident about. We also found that VILA's performance improves through a process we followed, which includes pre-training and supervised fine-tuning. We sampled 5% of the data from the pre-training phase to evaluate our approach. The images used were from existing datasets like Koyo and MMC4. In each iteration, we used the models trained in the previous round to generate new captions for half of the sampled Koyo images, while we did not recaption MMC4 due to its mixed features. We kept other settings consistent. Our comparisons of VILA across different iterations show that self-augmented data consistently improves model performance. Each new version, VILA from the next iteration, is better than the previous one, and this looping process progressively enhances performance. However, we notice that the self-augmentation technique remains effective only up to 3 rounds. By the 4th round, we reach a point of saturation where no further consistent improvements are observed. To push beyond these limits, we incorporated external spatial relations data and fine-tuned a spatial specialist visual language model. This approach allows us to extend the self-augmentation process further. By training a specialist model with domain-specific knowledge and using task-specific prompts during the recaptioning, we can enrich the captions with expert knowledge, thereby improving performance on benchmarks. We demonstrated that the VILA Spatial Relations Understanding Specialist focuses more on describing spatial information. The captions enhanced by this specialist retain the most visible details and provide more information about spatial relationships compared to the 4th round captions. This additional information includes not just object-to-object relationships but also the positioning and clear poses of key elements, which were not present in the spatial relation QA dataset. We believe this improvement results from combining knowledge from different parts of the training data, benefiting from both new task learning and the self-bootstrapping process. The effectiveness of these enriched captions is evident in our results. We integrated an additional 5% of COYO data recaptioned by the VILA Spatial Relations Specialist into the pre-training stage. Following the same supervised fine-tuning stage, we observed significant improvements in 5 out of 8 benchmarks. Section Summary. In this section, we describe our integration of specialty data with high-quality image captioning and instruction fine-tuning datasets to enhance model performance in narrative and task-specific knowledge. We detail our training process for various specialists, including spatial and OCR specialists, and highlight the effectiveness of our self-augmentation technique using VILA to improve caption quality, ultimately leading to better performance across multiple benchmarks. Section: Specialist-augmentation results. In this section, we shift our focus to our previous top-performing settings to investigate the importance of enhancing our VILA squared approach by using more pre-training data and larger models. This allows us to thoroughly examine the advantages of specialists. Following our VILA 1.5 release strategy, we utilize S2 with the Llama 3-8B instruct to improve the visual encoder by scaling it rather than just increasing the input resolution. We also employ a larger visual encoder, the Intern VIT6B, which has a similar number of parameters to the YE34B model, ensuring balanced training. We showcase the effectiveness of each specialist on a roughly 10% subset of the entire pre-training data mix and the 1.8 million SFT blend, as illustrated in our tables. Overall, we find that specialist visual language models show improvements across most visual question answering benchmarks. We then merge annotations from all 3 specialists into multi-round question-answer pairs for each image and retrain VILA. This collaboration among the specialists proves to be very effective, as scaling up to the complete pre-training set yields significant enhancements. Next, we conduct a thorough comparison with previous work across 10 major benchmarks, summarizing our findings in the tables. We note that we used a total of 25 million COYO data samples taken from the 700 million with the highest clip scores. We enhance the original short reel labels with multi-round question-answer pairs annotated by 3 specialists, all derived from 8B models. For the 40B models, we continue training from the Stage 2 checkpoints using a mix of 3.75 million recaptioned COYO data and a 200,000 caption dataset. We observe consistent quality improvements that can scale to the 40B VILA checkpoints. The detailed training methods for our 8B and 40B checkpoints are included in the appendix and will be released alongside the codebase. Notably, we find that the improved self-augmentation and specialist-augmentation training methods, supported by enhanced and refined datasets, enable VILA squared to significantly push the performance limits of VILA across nearly all benchmarks, consistent with the performance boosts we noted in our earlier analysis. Moreover, VILA squared now achieves state-of-the-art performance on the main MMMU test dataset leaderboard among all open-source models, without relying on proprietary datasets and solely using publicly available datasets. In terms of related work, we recognize that large language models, LLMs, began with the introduction of transformers and subsequent efforts to scale them. In the decoder-only paradigm, OpenAI launched the Generative Pre-trained Transformer (GPT) models, ranging from GPT-2 with 1.5 billion parameters to GPT-4 with 1.76 trillion parameters, showing that increasing parameters along with high-quality data can produce coherent and contextually relevant text across various fields. Transformer XL expanded the context window, allowing for better understanding of longer texts. Open-source LLMs have significantly advanced the field, including Llama 1, Llama 2, Llama 3, its instruction fine-tuned version Alpaca, and its chatbot version Vicuña. Other models have further pushed the limits of LLM capabilities, such as Mistral for generating coherent long-form text, Falcon scaling open-source LLMs to 180 billion parameters, Yi and DeepSeek for supervised fine-tuning to unlock multilingual capabilities, DBRX with a fine-grained mixture of experts architecture, and Gemini with a 10 million context window. The size of models is rapidly increasing, for instance, LLaMA3 at 400 billion parameters. Our work utilizes Llama 2 to 7B, Llama 3 to 8B, and Yi 34B as the backbone for our LLMs. Visual language models, VLMs, have also made significant strides in recent years, primarily due to pre-training visual and language models on large-scale internet data. CLIP trained a shared feature space for vision and language through contrastive learning on image caption data. Blip and Blip2 improved upon CLIP by using noisy pseudo-labels and expanded multimodal capabilities by aligning the pre-trained encoder with large language models. LLaVA and Instruct Blip showed that jointly training from a diverse collection of datasets as an instruction following task leads to strong generalization across various tasks. Cosmos 2 and PolyX significantly increased the pre-training data by pseudo-labeling bounding boxes from effective open vocabulary object detectors. They found that strong perception abilities, such as object detection and optical character recognition, translate to better high-level reasoning tasks like visual question answering. Our work broadens the scope of data scaling through our self-augmenting approach. Instead of directly using VLMs for data synthesis, we leverage specialist models with domain expertise in areas like object detection, spatial relations, and optical character recognition, which have great potential for contributing to the data collection process. In this paper, we investigate the potential of labeling large-scale internet image data using both self-augmentation techniques and models specialized in spatial relations. Regarding limitations, we focus on designing a self-augmented data curation pipeline and validating the 7B, 8B, and 40B models with 50 million data samples. We believe that larger models and more data could lead to improved VLM capabilities with self-augmenting abilities, and we plan to address these aspects in our future work.